As we discussed before, one of the most important reasons why we study wave is that a wave can allow energy to propagate, to transfer, without carrying particles along with it. So, as an example, let us focus on the wave on the string and look at how fast can energy transfer from one side of the wave to the other side. Okay, there are many different ways to look at it, but here is what we're going to do. Now imagine you install a counter. Okay, you install a counter here. This counter allows you to figure out, to measure how much energy propagates through it. Okay, so that's an energy counter. Now look at a certain time window. Okay, what time window? 1 period t. Why? Because you know the wave is periodic, right? It repeats itself after time t. So if you wait after time t, the exact same thing will repeat over and over again. Okay, so it is sufficient for us to look at what happens over 1 period t. So what happens over 1 period t? Well, you know the wave propagates forward by distance lambda, right? Over that 1 period time. So that means that if you start at this moment, you have a counter here, right? You start at this moment, t equal to 0. Okay, after 1 period, this part of the wave would have propagated to here. This distance from here to there is 1 wavelength. Okay, so this much wave from here to there has made its way through the energy counter. How much energy is carried by this part of the wave? Well, all I have to do then is to focus my attention on this part of the wave. Okay, I'm going to focus my attention on this part of the wave. In other words, 1 wavelength. Let me look at how much energy is stored, is carried by 1 wavelength of the wave on a string. Okay, speaking of energy, you know, this is mechanical energy, and it is the mechanical energy, the sum of the mechanical energy of each and every one of these simple harmonic oscillators, right? Or each segment of the wave. Now, if you focus your attention on one segment, say a segment right here, this segment has mechanical energy. It oscillates up and down, therefore it's got kinetic energy, right? It also has potential energy. Where did that come from, by the way? Well, it's because the string is stretched when a wave allows the string to bend like this, right? Otherwise, the string will be flat like this, right? If you stretch the string, you take an elastic string, you pull it, you stretch it, of course, you build potential energy into it, right? So, if you look at this one particular segment, okay, let's say the length is dx. This particular segment has kinetic energy and potential energy. Let's add them up, okay? So what do we get? We will be getting the mechanical energy of this little oscillator, okay? And then what we do is we add all these mechanical energies up for each and every one of these oscillators from here to there over 1 wavelength. All this energy will make its way through this energy counter over a period t. Then I can find the total amount of energy going through this counter over 1 period, right? Okay, now let us focus on the energy carried by this little oscillator of length dx. Okay, dE. And we know that equals dk plus du, right? This is a simple harmonic oscillator, okay? The kinetic energy and potential energy alternates, okay? But the sum is the same, okay? The sum is the same because, you know, for each simple harmonic oscillator, you know, the kinetic energy, potential energy, even though they both vary over time, the total amount of kinetic plus potential energy is always the same. What does that equal to? Well, that equals the maximum amount of potential energy. It is also equal to the maximum amount of kinetic energy, right? As we learned in discussion of the simple harmonic oscillator. So I don't really need to find kinetic energy and potential energy simultaneously because I know they add up to a constant which is equal to the maximum k or maximum u. Okay, so why don't I just calculate the maximum kinetic energy or the maximum potential energy that we know equals the total mechanical energy of this little oscillator. Why is this useful? Because the maximum energy, the maximum kinetic and maximum potential energy does not depend on time because it's a constant. Okay, I don't have to calculate both terms. Do I want to figure out maximum dk or maximum du? Which one is easier? Well, how about maximum dk? Because all I have to do is to find 1/2 mv squared for this little guy and maximize it, right? If I want to find du, then I have to look at how much the string gets stretched and so on, right? So that's a mess. I don't want to deal with that. I mean, I can, but I don't necessarily have to. So this really equals to dk maximum, right? Which equals 1/2 dm, the mass, times the speed of this oscillator going up and down, vy squared. Don't forget, I have to maximize it. Right? Okay. Let's simplify this calculation. What is dm? Isn't that mu dx? Okay, mu dx. Plus vy maximum squared. Okay, so basically what I do is take the maximum speed of this oscillator going up and down and then square it. What is the maximum speed? Now you'll recall we did a calculation of that. Okay. Let's put this slide back on. You see that? The speed, the velocity of this oscillator going up and down is negative omega a times cosine function, right? So as far as the maximum value is concerned, what is that equal to? Well, omega times a. Okay, that makes sense again because this is really just the maximum speed of a simple harmonic oscillator with angular frequency omega and amplitude a. So this is really just omega a maximum speed. Square it. Okay, square it. So what is this that we're getting? We are getting the total mechanical energy stored on a segment of the string between here and there of length dx. Okay, and the nice thing about our approach is that we're getting a number that does not depend on time at all. You compare this with the approach in the textbook. What they did was they calculated kinetic energy and potential kinetic energy at every moment for all of these oscillators, and it turns out that different oscillators do not reach maximum speed at the same moment. Of course, then you have to integrate over time or over space, whatever. We don't have to do that at all. Okay, we just make sure that we understand that each of these oscillators has a fixed amount of energy independent of time, and here is that total amount of energy. Okay, so this is the energy of this one oscillator, and if I add all these oscillators up from here and there over one wavelength, then I get the total amount of energy over one wavelength. Let's call it E lambda. Okay, this lambda means this is the total mechanical energy stored on one wavelength of the wave. That would be dE over one wavelength, right? That's so easy to calculate, much easier than the than the procedure that in a textbook they had to do a series integration. We don't have to do anything like that. Okay, so it is 1/2 mu. I'm taking all these constants out. Mu omega squared a squared, and then dx, right? This is the only thing that you have to integrate over. All these are constants. Dx, you must integrate over one wavelength, so you can go from any x to x plus lambda over any one period. Okay, now that of course is just lambda, isn't it? So we can get our final answer so quickly. 1/2 mu omega squared a squared lambda. Once again, what is this? This is the total energy carried by one wavelength of the wave. All this energy, because of the speed of propagation of wave, must pass through this energy counter over exactly one period. And therefore, the energy, the rate at which energy propagates over this one period, okay, that would be E over T. See that? Okay, so let's see what is that equal to. You have this expression and you divide it by T, right? So you take lambda over T. What's that? Oh, isn't that the speed of the wave? Okay, V, the speed of the wave, not Vy, but V, the speed of the wave. So isn't that equal to 1/2 mu omega squared a squared V, right? So what we're getting here is the average rate at which energy passes through this energy counter. In other words, it is the average rate at which energy is transferred by the wave on a string. And you see, this is proportional to a squared. Okay, we're going to use that fact a lot. So in other words, when you look at a wave compare two waves on a string. Okay, they have otherwise identical properties, same speed, same frequency, whatever. But one wave has twice the amplitude as the other. Then that wave will carry 4 times as much power as the first one because it's proportional to a squared. And that actually makes perfect sense because remember, the wave on a string is made of all these segments, right? Each segment is a simple harmonic oscillator whose total energy goes like amplitude squared. Okay, so when you double the amplitude, then you're quadrupling the energy carried by each segment. Of course, that also quadruples the energy transfer rate. So that makes perfect sense. Now let's give a name to this ratio. Okay, now let's give a name to this ratio, E over T. This is the rate at which energy is transferred by the wave on a string. And by definition, this really is the power delivered by that wave, right? If you have an energy window here, then over time t, you get this much energy going through. Isn't that the power delivered by this wave? So therefore, this is called the power carried by the wave. And we're going to use this expression a lot later. It is proportional to a squared, because that has to do with how much energy is carried by each oscillator. It is also proportional to v, the speed of the wave. And that makes sense because the faster the wave propagates, the faster energy is carried through. So this is how much energy is propagated per unit time, is transferred per unit time by this wave, without delivering any real mass over this window. Okay, no part of the string here actually goes through this window, yet energy is carried through. So this is a unique